Yes, Stefanos Kafudis, go ahead.
Oh, hello, can you hear me?
Yes.
Oh, thank you very much for the presentation. I enjoyed it very much. I would like you to comment some things regarding reciprocity and hermitivity. There was a slide, I believe. Sorry, I don't have the number. It should be the last slide of the third chapter.
So this one.
Oh, yeah, here it is. Yes, here it is. I mean, some comments regarding the conditions on whether reciprocity is satisfied or not.
So what it means here is that, I guess very briefly put, this slide, we're still in the static case. The material parameters don't depend on time in the setting.
Yes.
Reciprocity, I think one way to think about it is in terms of unidirectional band gaps. So the band gaps at alpha, they are different than the band gaps at minus alpha, so to speak.
Yeah.
It means that the frequencies will only propagate in one direction.
Yes.
Now, if you compare in the static case, if you compare alpha to minus alpha, they only differ by conjugation.
Yes.
If you take, it means that if you have real band gaps, so if you're somehow the difference of the if you look at the band functions at alpha compared to band functions at minus alpha, they will at most differ by the sign of the imaginary part, but the real part will always be the same because of the conjugation here. It means that if you specifically, if your frequencies are real, then you can never achieve broken reciprocity here if the imaginary part is 0.
Yes, I understand. But you talked about reciprocity in matters of unidirectivity of a band gap. Is the right way to think of reciprocity as that it is a fundamental difference between looking at a structure from the left or from the right?
Yes, which is, I think, equivalent.
This is equivalent. So the conclusion is that in the static case, a parity time symmetric structure is reciprocal.
Yes, exactly. We can never break reciprocity in the static case.
All right. Yes. Thank you very much. That covers my question. Thank you.
Wonderful. Thank you. Would somebody else like to jump in with a question? If not, while people are thinking, so the most of the results you presented here, you had kind of one particle. You had some at the end where you have multiple particles, right? So are there any like technical, theoretical challenges, should we say, that still need to be jumped over that are stopping you from doing like whatever really intricate geometries time modulated? Or is it just a case of doing it?
I mean, if you look at the theorem will apply regardless of how many particles you have inside the unit cell. The only thing that happens is that the size of the matrix will increase. So you have this essentially you have a system of coupled Hill equations, where inside of the matrix, the coefficient matrix is essentially given by the capacitance matrix. If you increase the number of particles, the size of the matrix will increase. I should say also that I didn't mention this, but for example, the broken reciprocity that I demonstrated here, it can only be achieved if you have 3 or more particles. So you cannot, if you have a single particle, if you have 2 particles, well, there are some symmetries of this particular system that means that you cannot break reciprocity. So you need at least 3 particles in this case.
Okay, because a system of 2 particles will always, is that still the case if your particles themselves are not symmetric?
Yes. It comes from the symmetry of the capacitance matrix, really. The capacitance matrix will always be well, not generalized, but the capacitance matrix itself will always be a Hermitian matrix. If it's a 2x2 matrix, it's a Hermitian one. There are some symmetry conditions with it, and you can prove that the band gaps that open here, they will always be symmetric in terms of plus alpha and minus alpha.
Okay, that's nice. Sebastian.
I've got some question regarding these band diagrams. It looks like a cusp, you know, when your acoustic band goes to the origin. So it doesn't go to the origin in a linear fashion. Can you comment on that, please?
I think if you zoom in around here, it will indeed be linear.
Okay.
The thing is that we are in the subwavelength regime here, which means that you have to kind of if you want the sound cone, the light cone will be a very steep one. So it looks like some square root or something like this, but
because there are some examples, very exotic examples for which it is a cusp at the origin, but usually so it's not this.
No, I don't think
okay. So the effective properties at the origin is just given by the slope of the acoustic band.
Yeah, exactly.
And okay, so I've got another. So obviously, as soon as it's time modulated, you have this shift on either side of the gamma point. So here, can you say something about the effective properties? So when it's time modulated.
So in this case, in this particular case, you see that the frequency is close to 0. They pick up an imaginary part.
Yes.
It means that they will be unstable. There will be modes which are either the frequencies which are close to 0. The corresponding modes will either decay or grow exponentially in time because of this imaginary part here. And I think somehow if you want to write down an effective equation here, well, the equation will be it will be either dissipative or it will have an exponentially growing term, so to speak.
And following on this discussion of effective properties, did you look at the case of time modulation, but with two parameters? Because here it's just a single parameter modulation, no? But you could have two parameters, and with a simultaneous. So can you say something on that?
So you mean that here I either consider rho or kappa?
Yeah.
So somehow the reason I did this, well, I try to make it as simple as possible in order to kind of really extract the phenomena that make, for example, exceptional points or unidirectional. I can, of course, we can put modulation of both kappa and rho. Somehow.
Because by doing this, you know. What will happen is that if you look here at your band diagram, if you have a two parameter time modulated stuff, you will increase non-reciprocity.
Yes,
that's a classical effect in the, especially in the low frequency regime. You see here in the low frequency regime, you cannot see any non-reciprocity. It's reciprocal in the, but as soon as it's doubly time modulated, if it's two parameters, then it will be also non-reciprocal in the near the zero frequency. Did you know that?
So somehow I'm not so sure. What will happen in this particular system, because for us
perhaps in your system that would not happen.
Really, somehow in my experience, in order to have this non-reciprocity, we really need to start at these degenerate points. So you have degenerate points here and here.
This is the classical one. Yes, that's but it's when you have just a single parameter which is modulated.
But in my experience, so I don't have systematic studies, but I tried around, you know, many different.
You did try already. You did try already.
And in my experience, this was kind of the most.
No, I mean, this is fantastic. It's absolutely fantastic. I mean, it's absolutely great. Yeah. Okay. And so, but do you experience? Alors, okay, here at the stop band level, it's clear the non-reciprocity, but I guess that you can already see it below that frequency. When does it kick off? You know, what is the onset of the non-reciprocity in terms of frequency? Did you look at that? At which frequency, you know, could you draw a line where you can start seeing the non-reciprocity?
So somehow, I mean, of course,
because you can see this kind of curve, you know, the shape it's tilted.
But I mean, somehow, as you say, somehow the shape is tilted.
Yeah.
But for me, reciprocity, because if you don't have a unidirectional band gap, then of course your modes will still propagate through the material.
Yeah.
They might propagate at a different momentum if you have a fixed frequency.
Yeah.
But they will still propagate somehow. So to me, somehow the most interesting thing is that if you really have a stop band, that the modes will no longer.
Yeah, but the effective, the group velocity is going to be different also, you know, this is important, these things. Huh?
Yeah. Okay, so of course, I mean, we can compute these explicitly, and we can,
and this is a nice effect, you know, it's really lovely to see this. This is also a hallmark of non-reciprocity. I mean, this is beautiful stuff. I mean, I really love, I mean, as Bryn knows, I really what you guys do. Okay, I don't have any more questions, except, I mean, that's the silly usual question. Can you, you know, export this in some kind of vector frame? I mean, can you see some extension for, you know, some kind of other governing equation, which is with vector valued unknowns and things like that?
So I think usually we should expect to have similar phenomena in different kind of vector valued, either Maxwell's equation or elasticity equations. The reason we chose the scalar wave equation is that it's really the kind of, it gives you the essence of the phenomena. It's the simplest case, but it already contains all the physics that you're asking for somehow. So of course, if we look at vector valued wave equations, we should only expect somehow more phenomena. At least that's how I see it.
Okay, I mean, this is absolutely fantastic. Thank you so much.
Thank you.
Very good, thank you, Seb. We have plenty of time for more questions. If anybody wants to ask one, please go ahead. Otherwise, I will keep rattling on through the things that I thought of while Erik was talking. So, I mean, one thing I thought was when you were talking about how, so my question was, do K gaps and band gaps behave in the same way, essentially?
Yep.
So let's say you're in a K gap where the imaginary part is negative, so you know the thing's going to decay, you know the mode's going to decay. If you, like in practice, if you built this thing and you had it, you sent a wave and it decayed, like, would you be able to see the difference between the two structures? Like if one was in a K gap and one was in a band gap?
Yeah, so I mean, somehow a band gap is a set of frequencies. It's a set of frequencies such that regardless of the momentum, the wave will decay.
Sure.
The K gap is kind of the other way around. It's a set of momenta that regardless of the frequency, the wave will decay. So I think if you fix a certain frequency, a certain momenta, you send a wave. It only depends. In that case, it only depends on. Well, you will not be able to really see it, but if you look in the range of all possible frequencies or all possible momenta, then you will be able to see the difference.
Yeah, sure, makes sense. I had a very specific question to the third slide of your time modulated section.
Yeah.
This was just me understanding. Yeah, that one. So you said, so here we've got a coupled system of Helmholtz equations.
Yep.
How are they? Where's the coupling? How are they coupled?
Yeah. Okay. So sorry, I should have maybe emphasized a bit further. So if you look at this V star and V double star, it's defined as a convolution.
Yeah.
So essentially, you have to take in order to compute them, you have to take the Fourier coefficients of this guy. You know, you multiply and you sum them up.
Yeah.
And when you sum them up, of course, you will have a sum over n. And through this one, V star, depends on Vn, but it also depends on all other V. So it depends on Vn minus 1 and Vn plus 1 and so on. So this quantity here, it depends on all the V, so to speak.
So the convolution is in space or time? Space.
It's convolution, well, in time, really.
Okay.
So it's convolution over n, so to speak. It's sum over n, this guy times this guy, Fourier coefficients of this guy. So up here we have Helmholtz equation of V. Down here we have Helmholtz, again, some kind of Helmholtz equation, but these guys, they depend on all of these guys. Yeah.
Okay. And then I had when you had your main theorem, which is one of the adjacent slides to this.
Yes.
You had so you said the reasons starting PDE has space and time, and the reason you're able to get rid of space is because firstly, do you agree that the reason you're able to get rid of space is because the perturbations are spatially compact, so you can integrate them out?
Somehow, not quite. Somehow my way of thinking about this is something along the lines that as functions of x, your eigenmodes, there will be approximately constant inside of each resonator. So you're not really looking at the PDE problem in space, you're really looking at a discrete problem in space, because your solution only depends on the discrete values inside of each resonator. And this is, I mean, in the static case, it's very clear how that happens. In the time modulated case, something quite similar happens, where again, now these functions V star, they will be the constant ones because they are the ones that have the Neumann conditions.
I see.
So the V star will be approximately constant, and then if we know these constant values, then we know exactly what is the. So it's kind of discrete in space, so to speak.
Yeah, sure. Okay, because my follow-up question was going to be if your time variations were not like these Fourier modes, but they were similarly like piecewise constant compact.
Yep.
Could you do the same thing and get a time capacitance matrix?
So that's a good question. I think so. I should mention that the analysis behind this theorem really assume that the Fourier modes are smooth. And sorry, it really assumes that the time modulation is smooth. So things like a sudden jump would not be captured in this theorem. But of course, I mean, we have things like we have things like time reflection, for example, and it would be interesting to generalize this setting to the more general case where we have non-smooth time-dependent coefficients.
Okay, very nice. I have at least one more question, but if anybody else would like to jump in, now is a perfect time for you to interrupt. Some other thoughts were about your exceptional points. We know that for the exceptional points we've seen occurring from spatial non-Hermitian variation, you get these nice enhanced sensing response, and you can do exciting things with them. Can you do the same with these ones?
We haven't tried, but we expect so.
Yeah.
So somehow we have the exceptional points, and the remarkable phenomena associated to exceptional points, well, they really come from this kind of deficiency of the matrix, if you want. And in this case, you have a similar deficiency. So somehow the system around these exceptional points should be similar to the static case. But this I think would be kind of interesting to look closer to see what kind of physics do you have around these exceptional points.
Sure, because I agree that it's qualitatively exactly similar, and so I agree it should behave the same. But the matrix that's singular is not the capacitance matrix coming from space, right? It's
exactly.
it's this system from your coupled system of Hammers. Okay.
Yeah.
And so does it? I mean, I think you've already answered the question, but presumably at these exceptional points, you get the same thing where it's not diagonalizable. It's got a Jordan normal form with diagonal. Okay, fine.
Yeah, so and that is not true in terms of the block modes of the solutions to the ODE equation, if you want. And of course, in the static case, it's much easier because we just have, the eigenmodes are just vectors basically. In this case, the eigenmodes that we have, they are solutions to an ODE equation. So we have a basis of function to the solutions of the ODE. Well, at this point, the basis becomes degenerate.
Yeah, sure.
Deficient. Yeah.
Cool, very nice. So does anybody else have any other questions they'd like to ask? So the only other question I had is very speculative, which is you have this, and just because it reminded me of exactly what we're seeing with this, exactly what we were just talking about with these exceptional points and the enhanced sensing response that you can do, or that you can make use of. This behavior where you have, I think it was on your next but one slide or something, where you have this either linear or quadratic behavior as a function of epsilon, depending on whether you have a degenerate point or not. Do you have any ideas about how this can similarly be leveraged to give something very useful?
So somehow the way I see it is that in order to see the phenomena, we should put ourselves at degenerate points. Because if we have a reasonably small time modulation and we are away from the degenerate points, we will not see so much somehow. Because here it's quadratic, it's much smaller. Here it's linear, we will be able to see the phenomena much more clearly somehow. But really somehow it comes from this perturbation factor. If you make it complex, you can get exceptional points, you can get band gaps, K gaps, like we have here. The perturbation term is complex. We get exceptional points here, and in between we have K gaps. If it's a real number, well, then it depends. If it's a real number, then it means that we will have opening of band gaps. And I mean, this is like, I think, any kind of phenomena that, well, for example, topological phenomena, it might happen also here. Topological phenomena, we start, for example, with a Dirac cone. We open the cone into topologically distinct topological phases. Well, here it's very easy to see that, well, we can create degeneracies. We can open the degeneracies. Then we might be able to tailor the topological behavior, for example, through these coefficients, basically. So how this linear modulation looks like. So somehow to me, that would be, of course, very vaguely put, but that could be an interesting further direction to look at.
Sure, very nice. Very, very nice. Thank you again, Erik.
Right, thank you.
So unless there are any final questions, now is the time to shout. If not, so thanks again, Erik. Thank you everyone for coming. Let's draw this to a close. So Sebastian, I assume there's another seminar next week?
Oh yes. Who will be the let us see. Agenda. Oh yeah. So next week will be Mohsen Ramani. I don't have actually any title yet, but this guy is from Nottingham Trent University in UK. So information coming soon, I guess. Yeah, I just want to say again that I really enjoyed this talk because I love this stuff on time modulated media. It's really fun.
Thank you.
And it's always great to see the group of Habib getting interested in what physicists do.
Yeah, I think there are many things left to do in this field, and somehow for us we have many different directions that we want to take this in. So I think it's really fun, it's really interesting, and there's a lot of physics to do here. Yeah.
And thank you very much, Mr. Chairman.
No problem, Seb, anytime. Right, speak to you soon, both of you. Been a pleasure.
Yeah.
And everyone else.
Thanks for hosting, and yeah, bye.
See you, everyone.